Have you ever wondered why aluminum oxidizes faster than iron, but doesn't really rust? That's because aluminum instantly forms a thin, tightly packed oxide layer that seals the surface, stopping oxygen from diffusing any further. Or think about your carbonated drink bottles. They're made of polyethylene terephthalate, PET, plastic. But because PET slows down the diffusion of carbon dioxide, so your drink stays fizzy for longer. And how do we make steel surfaces harder? Through processes like carburizing and nitriding, where carbon or nitrogen atoms diffuse into the metal surface, increasing its hardness and wear resistance. Even optical fibers use diffusion control. Their polymer coatings prevent moisture diffusion, protecting the glass core and keeping your internet signal stable and strong. Different materials, different purposes, but they all rely on one powerful principle that governs how atoms and molecules move: diffusion. Think of perfume spreading in a room. Without any fan, molecules drift from crowded regions to emptier ones. This occurs due to diffusion. Adolf Eugen Fick in 1855 introduces the Fick's Law of Diffusion, which tells us how strong that flow is. Here we'll see the diffusion from mathematical point of view, and we'll know about Fick's first law of diffusion. Diffusion refers to the net flux of any species depending upon thermal energy and concentration gradient. In materials processing technologies, control over the diffusion of atoms, ions, and molecules is the key factor. The rate of diffusion flux is frequently expressed as a diffusion flux, J, defined as the mass m, or, equivalently, the number of atoms, diffusing through and perpendicular to a unit cross-sectional area, A, per unit of time, T. Flux is also directly proportional to concentration gradient, and can be written as J equal to minus d multiplied by dc divided by dx. The minus sign means flux points from high to low concentration. Fick's first law relates diffusive flux to the concentration gradient. Within the solid, when concentration C versus position x is plotted, the resulting curve is termed as the concentration profile. The slope at a particular point on this curve is the concentration gradient. Steeper gradients or larger d give larger flux. This is being shown in the graphical form as well. If the diffusion flux does not change with time, a steady-state condition exists. One practical example of steady-state diffusion is found in the purification of hydrogen gas through thin metal foil. This process can be realized by the graph shown, where larger number of atoms showcases impure hydrogen gas. Red plane showcases the thin palladium metal foil. The hydrogen selectively diffuses through the metal foil to the opposite side, which is maintained at a constant and lower hydrogen pressure. The pure hydrogen atoms collecting down the line are shown in graph by two green color atoms. Fick's first law is the twin of Ohm's and Fourier's laws. In Fick's law, flux is proportional to a concentration gradient, pointing downhill. In Ohm's law, current density J flows down towards decreasing potential V with conductivity, sigma. A steep potential drop drives bigger current, just like a steep concentration drop drives bigger diffusion. Similarly, in Fourier's law of heat conduction, heat flux, Q, goes from hot to cold with thermal conductivity, K. Diffusivity is a thermally activated process, so it rises exponentially with temperature and is described by an Arrhenius relation. Taking natural logs gives us an equation which resembles with the straight line equation. If we plot natural log of d and inverse of temperature, we get a line with decreasing slope where slope corresponds to minus q divided by gas constant, R. Thus, with higher temperature there is increase in thermal energy which helps to cross the activation barrier, leading to higher diffusivity. Thus, I hope this video has given a clear understanding of diffusion and mathematical expression of Fick's first law of diffusion. Thank you for watching.